Einstein's equations contain a strange mathematical loophole. They forbid ordinary mass from accelerating to light speed, but they don't explicitly ban particles that start out moving faster than light. These are tachyons. But attempting to fit a superluminal particle into our current understanding of physics completely shatters the standard model. This chart shows why. On the left, an ordinary particle has a minimum energy gap. On the right, the tachyonic relation reveals a kinematic gap. Even worse, those downward curving red branches plunge infinitely. A single tachyon would trigger a runaway collapse, instantly destroying the vacuum. Then there is the timeline. Because these particles outrun light, a moving observer could see a tachyon arrive before it was ever sent. This creates a causality loop, effectively allowing a message to be coded into the past. Because of these pathologies, physicists spent decades dismissing tachyons as mathematical artifacts, glitches in the equations that couldn't possibly be real. Yet tachyonic terms appear naturally in our most successful theories, from the Higgs mechanism to string theory. Foundational thinkers like E.C.G. Sudarshan, pictured here, argued that relativity itself doesn't forbid these particles. Our interpretation of them is what's incomplete. The problem may not lie with the particle, but with our map of time. We have been trying to calculate superluminal motion using a mathematical framework that only accounts for a single, forward-moving timeline. To resolve the paradox, we have to upgrade our quantum architecture to include the missing half of the equation, backward time evolution. Instead of a single line of history, a new proposal suggests that physical states exist in a doubled Hilbert space. Every state is defined across two sectors simultaneously, a forward time sector and a backward time conjugate. This schematic shows how the space is built. The total Hilbert space splits into future and past sectors, linked by a bidirectional constraint, a handshake between directions. This creates a stable vacuum through the indefinite eta metric, ensuring consistent evolution. In this doubled architecture, the negative energy in the backward sector exactly balances the positive energy in the forward sector. The net energy expectation of the vacuum becomes zero. By expanding the state space, we obtain a stable environment where tachyons can exist without causing a catastrophic collapse. This redefines what a tachyon actually is. It isn't a physical bullet flying through space. In this model, a tachyon is a boundary-mediated excitation, a structural link that holds the two temporal sectors together. This diagram compares a standard quantum contour on the left with the projected contour for a tachyonic sector on the right. By using this specific projection, we isolate the auxiliary tachyonic modes from our observable measurements. Because they act as boundary states and not free-moving signals, they cannot transmit usable information backward into the past. This effectively neutralizes the causality objection that sidelined tachyons for a century. Tachyons are not information carriers, they are constraint carriers that define which histories are physically allowed. This framework offers a new look at the Big Bang. It suggests that at the earliest moment of existence, the universe was in a pre-causal phase where time had no fixed direction and tachyonic modes were directionless and unfixed. The theory posits that cosmic inflation was the relaxation of this initial instability. As the universe transitioned into the stable, dual-sector architecture we inhabit today, the symmetry broke, and that sudden relaxation released the energy that fueled the Big Bang. We don't see tachyons today because their transition from an unfixed state to a stable, bidirectional structure is what birthed our one-way arrow of time. To move from speculation to fact, this theory must survive these four failure modes. It has to provide non-trivial commutators and maintain observable unitarity. Otherwise, it fails as a valid quantum field theory. Evidence could be hidden in the background of the universe, indirect signatures in vacuum fluctuation noise, anisotropies in the cosmic microwave background, or non-local correlations that current models can't account for. If this architecture is correct, causality is not a bedrock law of physics. It is an emergent feature of a bidirectional universe, a continuous handshake between the past and the future.